Welcome to Quantitative Methods and Statistics. In this first module, we are going to lay down the essential knowledge you need for understanding both classical and advanced econometric methods. This isn't just about abstract theory, it's about tools you can apply to real-world data, in economics, business, policy analysis, and beyond. By the end of this module, you will not only understand what each method is, but also why it works, when to use it, and how to interpret the results in a practical way. 1. Introduction to Econometric Analysis. Econometrics is the application of statistical techniques to economic data to give empirical content to economic relationships. It helps us test economic theories, estimate relationships between different variables, forecast future trends, evaluate whether policies work as intended. Think of an economist who claims that increased education leads to higher income. Econometrics allows us to test that statement with actual data, taking into account other factors that may influence income, measuring uncertainty, and determining whether the relationship is real or coincidental. Objectives of econometric analysis. By the end of this module, you should be able to distinguish between correlation and causation, understand the different types of data used in econometrics, build and interpret regression models, recognize when the assumptions behind a model are violated, apply statistical inference to test hypotheses, prepare for more advanced estimation techniques covered in the next module. 2. Correlation versus causation. One of the most common mistakes in interpreting data is confusing correlation with causation. Correlation means that two variables move together in some predictable way. Causation means that a change in one variable directly causes a change in another. For example, suppose we find that cities with more bicycles also have higher coffee sales. That does not mean bicycles cause people to drink more coffee. Both could be the result of a third factor, such as a culture of urban lifestyle, higher incomes, or climate. The purpose of econometrics is to move beyond simple correlations toward credible evidence of causal relationships, using careful model design, statistical controls, and sometimes experimental or quasi-experimental data. 3. Nature and structure of the data. Not all data are the same. The type of data we have determines what statistical tools we can use. A. Cross-sectional data. Data collected for different entities at the same point in time. Example, a household income survey carried out in 2024. Common issues, omitted variables and measurement errors. B. Time series data. Data collected over time for the same unit of observation. Example, monthly inflation rates from 1980 to 2025. Common issues, trends, seasonal patterns, and autocorrelation. C. Panel or longitudinal data. Data that combine both cross-sectional and time series aspects, observing multiple units over several time periods. Example, GDP growth rates for 50 countries from 1990 to 2025. Advantage, allows us to control for differences between units that do not change over time. 4. Conditional expectations and regression. The idea of a conditional expectation is central to econometrics. It describes the average value of one variable, given a specific value of another variable. Regression analysis builds on this by creating an equation that links a dependent variable, the one we want to explain, with one or more independent variables, the ones we think influence it. 5. Linear regression and the ordinary least squares estimator. The most common method of estimating a regression relationship is called ordinary least squares, or OLS for short. The basic idea is straightforward. We draw a line through the data that best captures the relationship between the dependent and independent variables, in a way that makes the differences between the actual data points and the predicted values as small as possible. 6. Algebraic properties of OLS. When certain conditions hold, OLS has desirable features. It produces estimates that are correct on average. Among all possible methods that produce estimates without bias, it has the smallest possible variability. The estimates are straightforward combinations of the observed data. 7. Goodness of fit. Goodness of fit tells us how well our regression line explains the variation in the dependent variable. The most widely used measure is called the R-squared, which tells us the proportion of the variation in the dependent variable explained by the independent variables in the model. However, A high R-squared does not necessarily mean the model is good, and it certainly does not prove causation. 8. Functional form in regression. Real-life relationships are often more complex than a simple straight line. We can account for this by using logarithms to capture proportional changes, including squared terms to capture curvature in the relationship, adding interaction terms to see how two variables might work together to influence the outcome. 9. Classical linear regression model assumptions. OLS produces the best possible result only if several key assumptions are met. The relationship between the variables is linear in the parameters. The sample is randomly drawn from the population. There is no exact linear relationship between the independent variables. The average value of the error term is 0, given the independent variables. The errors have the same variance across all observations. In time series data, the errors are not correlated across time. The errors are normally distributed. This is particularly important for small sample sizes. 10. Sampling distribution of the OLS estimator. When the assumptions are met, we can work out how the OLS estimates behave across repeated samples. This allows us to calculate how much uncertainty there is around each estimate. Test whether a variable has a statistically significant effect. Make predictions about future outcomes. 11. Large sample theory and asymptotics. When the sample size is large, we can rely on certain statistical properties, even if the data are not perfectly normal. This means that with large datasets, we can still make valid inferences without depending on strict small sample assumptions. 12. Non-spherical disturbances. Two common problems in regression involve the error term not behaving as assumed. Heteroskedasticity, the variability of the errors changes across observations. This does not bias the estimates, but it does make the standard errors unreliable. The fix is to use robust standard errors or other corrective techniques. Autocorrelation. In time series data, the errors are correlated across periods. This can lead to similar problems as heteroskedasticity and require specialized corrections. 13. Endogeneity and instrumental variables. Endogeneity occurs when one of the independent variables is related to the error term. This often happens due to omitted variables that should have been included in the model, measurement errors in the independent variables, simultaneous cause and effect relationships. One solution is to use instrumental variables, variables that are related to the problematic independent variable but unrelated to the error term. 14. Transition to Module 2. In this first module, we have introduced the logic of regression, explained the method of ordinary least squares, discussed the assumptions needed for it to work well, looked at what happens when those assumptions are violated, introduced the problem of endogeneity and the idea of instrumental variables. In Module 2, we will go further into advanced estimation methods, optimization techniques for finding the best estimates, maximum likelihood estimation and its properties, the generalized method of moments, brief introductions to Bayesian and nonparametric methods.